All right, welcome in. We are looking at the comparison tests, section 11.4, going through a WebAssign discussion here. So let's take it bite by bite. It's freezing up on me, but give me a second and try to shock it back to life. And here we are. Okay. Well, or maybe not. Come on. Okay. So suppose A sub n and B sub n are series with positive terms, and B sub n is known to be convergent. Well, if A sub n's are bigger than B sub n's, what can you say? Well, hey, if the B n's converge but the A n's are bigger, the A n's could definitely diverge, right? Convergent just means add to a finite number. Well, hey, just because the B n's add to a finite number, the A n's could be way bigger. They could be slightly bigger and still be convergent, but they could be way bigger and be divergent. No one could say. However, if the A n's are smaller, because we have that positivity criteria, the BNs would converge and place a bound on what the ANs could converge to. And so monotone convergence would give us convergence in this case. So this is an example of the direct comparison test. So in other words, less than finite is finite, but greater than finite could be finite or infinite. That's the main takeaway there. Similar story here. What if the BNs are the small ones, but the BNs diverge? Now we know the BNs swell to infinity because if you're adding up positive terms, there's no way to oscillate. There's only one way to go, swell to infinity. So if the BNs swell to infinity when you add them up and the ANs are bigger, they have no choice but to swell without bound as well. So the ANs would have to be divergent in this case, thanks to the comparison test. On the other hand, if the ANs were smaller than the BNs sum up to infinity. Well, maybe the ANs were just a tiny bit less than the BNs, and they still swelled to infinity. Or maybe the ANs were a lot less than the BNs, and they added to something a lot less than the BNs. Maybe they added to something that was finite. So the ANs could converge, the ANs could diverge. In other words, greater than infinite, necessarily infinite, less than infinite, could be finite or could be infinite, depending. And that's the takeaway there. Determine whether this series converges or diverges. Well, here, we could use a direct comparison test. Note that 9 that's upstairs. If you took that 9 away, you'd have a new series that had smaller terms. And that series with smaller terms would simplify because the n's would cancel, and you just get 1 over root n. Well, that smaller thing with the 1 over root n already diverges by the p-test. So if the smaller thing diverges, the bigger thing no doubt diverges. And so, yeah, we can use direct comparison to show that we are greater than a divergent p-series in this case, because we had 1 over square root n, or 1 over n to the 1/2. What about this next one? Can we use the comparison test here? Well, I don't think we can use the direct comparison test, because if we took the 2 away here, we'd get something smaller. The n could cancel with one of the n's down below in effect, and get us down to 1 over n to the 5th. But 1 over n to the 5th is convergent. So we expect convergence here, but greater than convergence tells us nothing. Greater than convergence could be convergent or divergent. And so what do we need to do? We need to use a limit comparison test here. So if I was going to use a limit comparison test, because we have n to the 6th downstairs and n upstairs, I would compare to 1 over n to the 5th. 1 over n to the 5th would give you everything that you need, because it would have the ratio of powers of n equivalent to the ratio of powers of n in this case. And if you run the limit comparison test out, assuming you have set up your comparison to have an equivalent ratio of n's upstairs and downstairs, you'll be in business. It will work every time, because you'll end up with an equal heavy expression as a result of the limit comparison test. Just to remember, here you're going to take a limit of an over bn, which is going to be a double-decker fraction, comparing the original fraction to the new fraction 1 over n to the 5th that you're comparing to. Right, 7 sine 3 over n. Now, definitely use the step-by-step here, because this one, it's a classic. It is not so apparently obvious how it plays out, but take it step by step, and you'll be able to make an appropriate comparison. It's just a cool example. I don't know how to say it any way other than that, and so take your time to go through this. Just enjoy it for the spectacle that it is. I would be very surprised if something like this ever showed up on a quiz or a test, but it's an oldie but a goodie. So good to know. Determine whether the series converges or diverges. Well, hey, here we are basically 1 over square root n squared, basically. Now the 3 and the 7, right, they become negligible as n gets big. And 1 over square root n squared is just 1 over n. And so if I was comparing here, I would compare 1 over n. And knowing that 1 over n is going to diverge, I would expect this to diverge as well. However, we mustn't just jump to conclusions. Here is an example, put a star by it, where WebAssign and their question asking sucks. They should be asking you, what are you comparing to? What test are you using? What is the limit you're comparing? What is the value that's popping out of that limit? And they are not. I don't know why. It is what it is. Definitely take your time here and go through a proper comparison test. You're going to have to take a limit comparison test of that. You're going to have to take a limit of a double-decker thing as n goes to infinity, but that double-decker thing is going to be chosen such that when you keep change flip, you'll get an equal heavy rational expression. Right, 1 over ln n. Now this one, I think we can do with direct comparison, because ln n's are small compared to n's. Look at a graph of f of x equals x. Look at a graph of f of x equals ln x. The ln x is concave down and lives below the graph of f of x equals x. And so the ln n's are less than the n's, and the 1 over n's already diverge. Well, if the 1 over n's diverge and you've got something less downstairs means bigger fraction popping out. Add up the first 5 terms of this. Compare it to the first 5 terms of sum 1 over n. See for yourself why this series is going to diverge, since you know that the sum 1 over n's diverge. And right, that's that. If the an's are a convergent series, then the sum of the sine of an's is also convergent. Is this true? We are going to have to go through a limit comparison test here. This is a good one. This is a really trippy example. Do a limit comparison test comparing these 2 examples. You will get a flashback to a famous fact from Calc 1 of sine x over x and its limit. That is, this is too good. So take your time, go through that limit comparison, and flash back to that fact from Calc 1. Here's another example where I don't foresee this showing up on a test anytime soon, but damn, this is a good one. So just soak it in while you're in the moment. And yeah, this is mathematically, this is a great example. Okay, what about this next one? Let's see here. We got 1 plus, the sine n is basically doing nothing, because the sine n is like only between 1 and minus 1. That e to the n, though, is getting gigantic. And so set up a limit comparison with 1 over e to the n. 1 over e to the n is geometric. The common ratio is 1 over e, and the convergence behavior is known from that. And so, yeah, definitely go through that. Again, WebAssign sucks in terms of how they are going about this. They should be like, what are you comparing to? What test are you using? The limit comparison test in this case. Like, what series are you comparing to? Like 1 over e to the n. Why 1 over e to the n? Because that sine n should be practically meaningless when that n gets gigantic, because that e to the n is just going to be enormous. And that sine n is practically going to be negligible. And you'll see that whenever you run the limit comparison. You'll get a conclusive result. Similar story here. That 6 downstairs is doing nothing for us. The 6n over 11n is doing all the heavy lifting. And so if we compare this through a limit to 6 to the n over 11 to the n, the double-decker will work out beautifully, and you'll end up with something quite nice. You'll see that this thing is basically the same in terms of its behavior thanks to the limit comparison test of 6 to the n over 11 to the n. But you want to take your time to go through that process, because when your test comes around, you're going to have to say what series evaluation tool, what series test you're using, and then you're going to have to apply it appropriately, considering the right limit and computing everything exactly. And so sometimes WebAssign is not great in terms of the question that it's providing. And boy, here is an example. So take your time, write this out, 6 to the n over to the 11 to n, take it one bite at a time. Determine whether this statement is true or false. This is the last one. So the BNs are the big ones. If the BNs diverge and the ANs diverge, don't know for sure, right? Because if the BNs diverge, maybe the ANs diverge, but maybe the ANs converge, and there's just no way of knowing, right? Because smaller than infinite could be infinite or could be finite. There's just no way of knowing. And so, once again, hammering down this subtlety of the comparison test. Boy, something like this, I could totally imagine this on a true-false question of a quiz or a test. This is a classic demonstration of do you get what the direct comparison test is all about. So setting that aside, that's a wrap on 11.4. Let's move on to 11.5.